You are about to find out why one of the most respected astrophysicists on the planet believes that Mars could be a death trap disguised as hope, and why even with all our advanced technology, we may never truly be able to call the red planet home. But before I reveal this devastating detail that Neil deGrasse Tyson shared, that completely changes our perspective on Martian colonization, I need to ask you a question that will define everything you are about to learn. And that question is, do you really think you would be able to survive on a planet that is constantly being bombarded by an invisible and lethal force that passes through your body at this very moment, while you breathe peacefully here on Earth, but that on Mars would transform every second of your existence into a cosmic Russian roulette, where your cells would be systematically destroyed without you being able to do absolutely anything to stop it? Because that is exactly what would happen. And Neil deGrasse Tyson, in one of his most incisive analyses of the future of humanity in space, revealed an aspect of Mars that most people simply ignore when they talk excitedly about building Martian cities and terraforming the planet red, turning it into a second Earth. And this detail has nothing to do with the lack of liquid water on the surface, or with the dust storms that can last for months, or even with the brutal temperature that plummets to -80 degrees Celsius during the Martian night, because all these are problems that theoretically we could solve with sufficiently advanced engineering. But what Tyson highlighted goes much deeper and touches on something so fundamental in planetary architecture that without solving it, any attempt at permanent colonization would essentially be building a sophisticated and expensive interplanetary cemetery where we would be condemning future generations to a slow and inevitable death. And if you are one of those who love unraveling the mysteries of the cosmos, like me, and want to understand why one of the greatest scientific communicators in the world is sounding this alarm about our Martian dreams, subscribe to the channel now, because we are going to dive deep into the real science behind this revelation. And I guarantee that after understanding what is really happening to Mars, you will never look at that red dot in the night sky the same way again, because the truth about the red planet is simultaneously fascinating and terrifying, ways you probably never imagined. And to fully understand this devastating detail that Tyson revealed, we must first take a journey through time and space back to approximately 4 billion years ago, when Mars was radically different from the frozen, dusty desert we know today. Because, believe it or not, the scientific evidence accumulated by decades of robotic missions shows us that ancient Mars was a place you would probably want to be. It was a world with vast oceans running across the surface, with rivers snaking through deep valleys, with an atmosphere thick enough to maintain stable liquid water, with perhaps even rain falling from the Martian sky, and with a climate that, although different from Earth, would be recognizable to us as a dynamic and potentially habitable planetary environment. And we know this not from speculation, but from hard data collected by the Curiosity and Perseverance rovers that found ancient riverbeds, minerals that only form in the presence of liquid water for long periods, chemical evidence of aquatic environments that have persisted for millions of years, and geological formations that are unequivocally the result of large-scale water erosion. So what the hell happened? How an entire planet went from a potentially habitable world with oceans and atmosphere to the barren, irradiated rock we see today. And this is where the story gets truly disturbing, because not only did Mars lose its water, it lost something much more fundamental, something that Earth possesses that protects all life on the surface of our planet right now. As you watch this, something that is so essential to the existence of complex life, that without it, our planet would probably be as barren as Mars is today, and that something is the global magnetic field. And when I say magnetic field, I'm not talking about something abstract or secondary. I'm talking about the invisible shield that surrounds our entire planet, generated by the movement of liquid iron in the Earth's outer core, approximately 3,000 kilometers below our feet, where temperatures of 5,000 degrees Celsius keep this metal in a liquid state, constantly in convective movement due to the residual heat from planetary formation and the radioactive decay of heavy elements. And this movement that we call a geomagnetic dynamo creates a magnetic field, magnetic that extends tens of thousands of kilometers into the space around the Earth, forming the magnetosphere, a protective bubble that deflects high-energy charged particles from the Sun and interstellar space. And Mars had exactly that. Billions of years ago, it had an active core, generating a robust magnetic field that protected its atmosphere and surface. But then, something catastrophic happened. The core of Mars began to cool faster than it should, because Mars is only about half the diameter of Earth, and about a tenth of our mass, which means its volume in relation to its surface area is much smaller. And in planetary physics, this is crucial, because smaller planets cool more quickly, as they have proportionally more surface to radiate heat, in relation to the internal volume that generates that heat. It is like comparing a small cup of coffee that cools in minutes with a large kettle that maintains the heat for hours. The difference in scale matters enormously, and as the Martian core cooled, the convective movement of the liquid iron gradually decreased, until at some point there are approximately 4 billion years. The magnetic dynamo of Mars simply stopped, the core solidified, the magnetic field collapsed, and in that moment, the fate of the planet was sealed in a way that is perhaps irreversible, because without the magnetic shield, Mars was completely exposed to what we call the YAB, solar wind, which is in fact a constant flow of charged particles, mainly protons and electrons, that the Sun ejects in all directions at speeds of 400 to 800 kilometers per second, carrying enough kinetic energy and radiation to literally rip atoms out of the Martian atmosphere one by one over millions of years. And that is exactly what happened. NASA's MAVEN probe, which has been orbiting Mars since 2014, has been measuring in real time how the solar wind is continually removing about 100 grams of Martian atmosphere. Per second, it may seem small, but over billions of years this has meant the loss of an atmosphere that was probably as dense as Earth's today, with only a fraction of a percent of that original density remaining. And here we come to the crucial point that Neil deGrasse Tyson emphasized so vehemently, and that most discussions, popular stories about Martian colonization, conveniently ignore: no magnetic field. Mars is not just a planet with a thin atmosphere. It is a planet where the entire surface is constantly being bathed in levels of radiation that are absolutely lethal to DNA-based life forms, like us. And when I say radiation, I'm not just talking about ultraviolet light, which is already problematic enough. I'm talking about galactic cosmic rays, which are atomic nuclei accelerated to speeds close to that of light by cataclysmic events like supernovae, and streaking through space, interstellar, with energies so absurd that when they collide with atoms, they can create cascades of secondary particles capable of penetrating meters of solid rock. And I'm talking about solar particle events, where the Sun occasionally ejects massive bursts of high-energy protons that in a matter of hours can increase the radiation levels on Mars by 200 times the normal levels, which are already dangerous. And the difference between Earth and Mars in this regard is simply dramatic. Here on Earth, our magnetosphere deflects 99% of this high-energy radiation before for it to reach the atmosphere, and the few cosmic rays that manage to penetrate still have to pass through the entire thickness of our atmosphere, which is equivalent to approximately 10 meters of water in terms of blocking capacity. So when they finally reach the surface, The radiation levels are low enough so that complex life can exist with only occasional repairable damage to DNA. And we have evolved here with sophisticated cellular DNA repair mechanisms precisely because, even on Earth, some radiation reaches us. But on Mars, the situation is radically different. And this discovery has impacted scientists all over the world. So I wonder, where are you watching from now? Comment on your city or country. Because it's incredible to think that we are all connected in this same universe, trying to better understand our place in it and the challenges we would face in expanding beyond our home planet. And these challenges on Mars are measured not in terms of discomfort or inconvenience, but in terms of accumulated radiation doses that literally determine how long a human being could survive. And the numbers are absolutely frightening. The average radiation dose on the surface of Mars is approximately 250 millisieverts per Earth year, compared to about 3 millisieverts per year that the average person receives here on Earth at sea level, which means that simply being on the surface of Mars without additional protection would expose you to more than 80 times the radiation you receive on Earth. And this is not radiation that you experience as heat or light. It is ionizing radiation that passes through your body, breaks chemical bonds in your DNA, creates free radicals that damage proteins and cell membranes, and essentially causes cumulative microscopic damage to every cell in your body. And contrary to what many people imagine, there is no safe level of radiation, there is only an acceptable level of risk. And each additional millisievert that you receive statistically increases your likelihood of developing cancer, of suffering damage to the central nervous system, of having cardiovascular problems, of experiencing tissue degeneration, and of accumulating mutations that can be passed on to future generations if you manage to live long enough to reproduce. And Neil deGrasse Tyson has been vocal about this, highlighting that we are not talking about a simple engineering problem like building pressurized habitats or life support systems. We are talking about a fundamental physical problem of planetary architecture that requires solutions on a scale that is perhaps beyond our current or foreseeable future technological capabilities. Because building structures with sufficient shielding against cosmic radiation on Mars would basically mean living permanently underground under meters and meters of Martian regolith or rock, which raises the philosophical question: if you have to live buried in underground tunnels under tons of rock to not die from radiation-induced cancer, are you really colonizing a planet? Or just creating an extremely expensive underground prison on another world? And even if we accept living like that, there is another problem that Tyson and other planetary scientists have highlighted. Without a magnetic field, there is no way Mars can maintain a thick atmosphere in the long term, even if we could, through advanced terraforming, release enough greenhouse gases to thicken the Martian atmosphere and increase the temperature. Even if we could somehow melt the polar ice caps and release the frozen carbon dioxide there. Even if we could import volatile-rich comets to add water and gases to the atmosphere, all of this would be temporary, because the solar wind would continue to remove this newly created atmosphere just as it removed the original atmosphere billions of years ago. Calculations show that any dense atmosphere we created on Mars would be removed on a scale of time of tens to hundreds of millions of years, which seems like a lot, but is a blink of an eye in geological terms, and would mean that we would essentially be trying to fill a leaky bucket by trying to maintain an atmosphere on a planet that is structurally incapable of retaining it without continually expending enormous energy and resources to replace what is constantly being lost. And here is something that makes it even more complex. Even if we decided to accept all of these challenges, even if we built elaborate underground cities with miles of rock above to block radiation, even if we developed closed systems, perfect recycling of air and water, even if we created underground agriculture with artificial lighting, we would still have to deal with the biological effects of Martian gravity, which is only 38% of Earth's gravity. And although this seems less dramatic than the radiation issue, decades of research in space stations have shown that reduced gravity causes loss of bone density at a rate of 1 to 2% per month muscular atrophy, including of the heart muscle redistribution of body fluids, which affects vision problems in the immune system and potentially irreversible changes in human development. And here is the most frightening problem. No, we know what would happen to a child conceived and gestated in Martian gravity. We have never tried this. We have no data. Whether a self-sustaining population could actually reproduce and raise healthy generations on Mars remains completely open. And this fundamental uncertainty is part of what led Neil deGrasse Tyson to be so skeptical about the grandiose Martian colonization plans we see being promoted by billionaire businessmen and space enthusiasts, because the difference between establishing a temporary, scientific outpost on Mars, where astronauts rotate on missions of a few years, and truly colonizing the planet, in the sense of creating a permanent, self-sufficient civilization, is astronomical, both literally and figuratively. And Tyson has argued that perhaps we are focusing on the wrong planet, for the wrong reason that perhaps our obsession with Mars is more about cultural romance, influenced by decades of science fiction, than about rational analysis of the physical realities involved. And he raises an interesting point if our goal is to preserve humanity against existential risks on Earth. Why not invest those trillions of dollars in protecting and healing our own planet that already has everything we need? Breathable atmosphere, abundant water, protective magnetic field, adequate gravity, tolerable temperature, functional ecosystems, rather than trying to create a vastly inferior and precarious version of this on a hostile world millions of miles away. And this question is not coming from someone who is against space exploration. On the contrary, Tyson has dedicated his life to inspiring people about the cosmos. But it is coming from a scientist who understands the scales of difficulty involved, and who is concerned that we are selling people a technological fantasy that diverts resources and attention from solvable Earth problems as we pursue a Martian dream that may be fundamentally impossible in the ways we imagine. And here we need to make a crucial distinction between what is technically possible and what is practically and ethically viable. Yes, it is technically possible to send humans to Mars. We already have the basic physics for it. Yes, it is possible to build habitats that would keep astronauts alive for limited periods on Mars. We already know how to do this in principle, but creating a permanent, self-sufficient, multi-generational civilization on Mars, which is what colonization really means, in the sense that the word implies it faces barriers that go far beyond. Simple challenges of engineering are barriers imposed by the fundamental physics of how planets work, the biology of how complex DNA-based organisms respond to radiation and gravity environments, the geology of how planetary magnetic fields are generated, and the economics of how much energy and resources would be needed to maintain a permanent human presence in such a hostile environment. And the deeper scientists study these problems, the more they realize that we are not just facing technical obstacles that can be overcome with smarter engineering or more resources. We are facing fundamental limitations of physical reality that govern how planets and life work. And this leads us to one conclusion, uncomfortable, that Neil deGrasse Tyson has articulated and that many in the planetary scientific community agree with but are hesitant to say too loudly because it seems defeatist or pessimistic. But that needs to be said honestly if we are to have realistic conversations about humanity's future in space, and that conclusion is that Mars in its current form may simply not be colonizable in the traditional sense of the word, not without first solving the fundamental problem of the absence of a magnetic field And solving that problem doesn't just mean protecting individual habitats. It means recreating an entire planetary magnetic field. And here we enter the territory of planetary engineering on scales that make our current largest engineering projects look like children's toys. Because how would you generate a magnetic field for an entire planet? Some theoretical proposals exist. The best known involves placing an artificial magnetic satellite at the Lagrange point between Mars and the Sun, that point where the gravity of the Sun and Mars balance, which would create a localized magnetic field strong enough to deflect the solar wind around Mars, essentially creating an artificial magnetosphere, and computer simulations suggest that this could work in theory, allowing Mars to gradually, over decades or centuries, recover a denser atmosphere as gases were released from the ground, and polar ice caps without being immediately removed by the solar wind. But building such a device would require a magnetic generator with a field of absurd intensity, powered probably by a massive nuclear reactor or solar panels the size of cities operating continuously for centuries. And the energetic and financial cost would be measured not in billions, but in trillions of dollars, and we would have to keep it running in perpetuity, because the moment it turned off, the solar wind would once again remove the atmosphere. And we would have to do all of this before we even started to real colonization, which means an astronomical investment up front with no guaranteed return. Another even more radical proposal suggests literally reheating the core of Mars by detonating nuclear devices in the deep mantle to restart convection and regenerating the magnetic dynamo, but this is so far beyond our current technological capabilities that it borders on pure science fiction. It would require not only the ability to drill tens or hundreds of kilometers beneath the Martian surface, but also to understand precisely how to manipulate the convection of an entire planetary core without catastrophic unforeseen consequences. And even if we could do this, it would probably take millions of years for the core to cool to a state where it sustained stable convection, i.e., we would not see results on any humanly relevant timescale. So when Neil deGrasse Tyson talks about this devastating detail about Mars, he is referring to this fundamental reality that the planet has lost its magnetic protection, and with it, its ability to be a habitable world on the surface. And recovering this, if it is possible, is so far beyond our current capabilities that planning permanent colonization without resolving this first can be dangerously naive. And here is where the conversation gets even more interesting, because some scientists argue that we may not need to colonize the surface of Mars. Perhaps true Martian colonization will happen in the lava tubes, vast natural tunnels formed by ancient lava flows that extend for tens of kilometers beneath the Martian surface, where the rock above would provide natural protection against radiation, or perhaps in habitats built into deep canyons like Valles Marineris, which is over 7 kilometers deep in some places, where the canyon walls would offer some shielding against high-energy particles. But this brings us back to the same philosophical question. If your Martian civilization consists of people living permanently in tunnels or deep canyons without ever being able to walk freely under the Martian sky, without suits, heavy radiation, without ever being able to have surface agriculture, without ever being able to build open-air cities like we do on Earth, have you actually colonized a planet or just created survival habitats in a permanently hostile environment? And there is a genuine debate in the scientific community about this. Some argue that any permanent human presence outside of Earth, regardless of how limited, counts as successful colonization, because it establishes redundancy for the human species. Others argue that unless we can create truly self-sufficient and prosperous non-survival societies relying on constant supplies from Earth, we have not achieved true colonization in the meaningful sense of the word. And this distinction matters because it determines what kind of resources we invest and what expectations we set. And Neil deGrasse Tyson tends to align himself with the second view, arguing that we need to be honest about what is actually possible rather than peddling utopian visions of shiny Martian cities that may never materialize in the ways we imagine. And it is worth noting that Tyson is not alone in this assessment. Many planetary scientists and space biologists share these concerns but are less vocal publicly because there is a cultural bias, especially in certain technology circles and entrepreneurship, of treating skepticism about Martian colonization as short-sightedness or excessive pessimism, when in fact it is just sober analysis of the physical realities involved, and those physical realities do not change based on how excited we are or how much money we invest. Some problems have no technological solutions, at least not on humanly relevant timescales. And the absence of a Martian magnetic field could be one of those problems, or at least a problem that requires centuries of technological development before we can adequately address it. So what we do with that information, we rule out completely. Embrace the idea of human presence on Mars, and there is something between completely giving up and promoting unrealistic fantasies of colonization. And Tyson and many scientists suggest that yes, we should absolutely continue exploring Mars with robots, scientific missions, orbiters, increasingly sophisticated rovers, because the scientific value is immense. Mars is a natural laboratory for understanding planetary evolution, climate change, atmospheric loss, and perhaps even history of life beyond Earth. And we should eventually send humans to Mars for short-term scientific missions. Think about research bases like the ones we have in Antarctica, where scientists rotate in shifts of a few months or years, but return home because no one actually colonizes Antarctica in the sense of establishing multi-generational families there permanently, because the environment is very hostile and Mars is orders of magnitude more hostile than Antarctica. And perhaps that is the most realistic model for human presence on Mars in the coming decades or even centuries, permanently manned. Research bases, but with staff rotation, co-scientific knowledge being built gradually, survival technologies being tested and refined, and who knows, eventually, if we develop sufficiently advanced technologies, we may attempt the large-scale planetary engineering needed to make Mars genuinely habitable, but that would be a project of centuries or millennia, not something we will see in our lifetimes or in the lifetimes of our grandchildren. And we need to be honest about those timescales rather than promising Martian cities in 20 or 30 years, as some have done, because such promises are not only unrealistic, they are potentially harmful because they create false expectations and divert resources of more viable projects, and can lead to ill-informed decisions in both space policy and private investment. And here is something that is often lost in these discussions: space exploration and colonization is not a binary choice between Mars or nothing. There are many other destinations in the solar system that may be more suitable for long-term human presence than Mars. The Moon, for example, is only a 3-day journey from Earth, rather than months, making rescue and resupply much more viable. And although it also has no magnetic field, its radiation levels are comparable to Mars, but with the advantage massive proximity, making it much more practical to build and maintain habitats there. And there are fascinating proposals for floating habitats on Venus, not on the infernal surface that would melt lead, but in the upper atmosphere at about 50 kilometers altitude, where the temperature is 25 degrees Celsius. The atmospheric pressure is similar to that of Earth at sea level, and the dense carbon dioxide atmosphere would provide excellent protection against cosmic radiation, and the moons of Jupiter and Saturn, especially Europa and Enceladus, which have subsurface oceans of water, liquid beneath its ice crusts, may be more interesting targets for searching for extraterrestrial life than Mars ever was, and there are even proposals for cylindrical-shaped space habitats rotating to create artificial gravity through centrifugal force that could be built at Lagrange points or in orbit around resource-rich asteroids, allowing permanent human presence in space without relying on hostile planetary surfaces. So when we think about humanity's future beyond Earth, perhaps we need to expand our imagination beyond the specific cultural narrative of colonizing planets that has been so reinforced by 20th-century science fiction. Perhaps the future of humanity in space will not look like pioneers marching across the surface of Mars, but rather a diversity of specialized habitats in different locations in the solar system, each taking advantage of the unique advantages of that specific location. Some around the Moon, others floating on Venus, some on asteroids, mining resources, others in orbital space stations, and yes, eventually perhaps some on Mars, but probably underground or in heavily armored structures, recognizing the fundamental limitations of that environment rather than pretending they do not exist. And this more diverse and pragmatic vision of expansion humanity through the solar system may actually be more resilient and sustainable than putting all our eggs in the Martian basket if, you'll pardon the terrestrial analogy, and Neil deGrasse Tyson has argued for this more nuanced approach by recognizing that Mars has a special cultural and symbolic appeal as humanity's obvious next step into the cosmos, but insisting that we need to balance that emotional appeal with rational assessment of the scientific realities involved, because the cosmos doesn't care about our dreams and fantasies. The cosmos operates according to indifferent and inflexible physical laws, and our success in expanding beyond Earth will depend on our ability to work within these laws, not on imagining that our technology or determination can somehow transcend them. And that is perhaps the most important lesson from the devastating detail that Tyson revealed about Mars, the lesson of cosmic humility, that even with all our ingenuity and technology, we are still creatures deeply dependent on the specific planetary conditions that formed us, and that recreating these conditions elsewhere may be much more difficult than we imagine, perhaps even impossible with the technologies we can predict. And this should not be depressing. It should be inspiring because it reminds us of how extraordinary and precious our home planet is, with its magnetic field, generated by a molten iron core spinning thousands of miles beneath our feet, with its atmosphere held in place by enough gravity and protected by that invisible magnetic shield, with its vast oceans and water cycles, with its incredibly complex ecosystems. Developed over billions of years of evolution, Earth is not just another planet. Rocky is a very rare oasis of perfectly balanced conditions in a vast cosmos that is mostly hostile to life as we know it. And perhaps before we try to colonize other worlds, we should become better guardians of this world that we already have. And if these discoveries have blown your mind as much as mine, if you now look at Mars with a mixture of fascination and respect for the immense barriers it represents, subscribe to the channel and turn on notifications because we have many more mysteries of the universe to unravel together. And the journey of understanding our place in the cosmos is just beginning. And that journey teaches us that each planet has its own history, its own evolution, its own physical personality, determined by the conditions of its formation. And Mars is a monument to planetary processes that have failed in a way that has irreversibly defined the fate of that world, because once a planet loses its magnetic dynamo, once the core cools below the point where it can maintain convection, there is no going back. At least not without technological intervention on scales that defy the imagination, and that makes us question other assumptions we have about planetary habitability, because we tend to focus on habitable zones around stars that distance range where temperatures would allow liquid water on the surface, and we assume that any rocky planet in that zone is potentially habitable, but the history of Mars teaches us that habitability is not just about distance from the star. It's about enough planetary mass to keep a core active for billions of years. It's about the right internal composition to generate a magnetic dynamo. It's about having plate tectonics to recycle carbon and regulate climate in the long term. It's about 1,000 planetary details that have to line up perfectly. And suddenly, we realize that truly long-term habitable planets may be much rarer than we thought. Earth may be not just lucky, but extraordinarily lucky to have maintained all of these stable conditions for 4.5 billion years, allowing life to not only arise, but evolve from single-celled organisms to the incredible complexity we see today. And this realization fundamentally changes how we think about our place in the universe. Because if habitable planets are really that rare, if the combination of characteristics needed to support complex life, long-term is so specific, so maybe intelligent life is correspondingly rarer than we expected. Maybe the great silence we observe when we look for extraterrestrial civilizations is not because they inevitably self-destruct, or because we are looking in the wrong places, but simply because the path from simple chemistry to conscious complexity requires so many specific planetary conditions maintained for so long that it happens only occasionally, even in a galaxy with hundreds of billions of stars. And this makes our existence not less significant, but more so because it means that we are potentially among the rare experiments in the universe to look at itself, to ask questions about its own nature of developing science and philosophy and art and everything that makes consciousness precious. And that rarity implies responsibility. The responsibility to preserve and protect what we have. The responsibility not to assume that we will always have an easy planet B to escape to if we mess this one up. The responsibility to recognize that our dreams of cosmic expansion, while inspiring, cannot replace the essential work of keeping habitable the only world we know for sure can support our existence. And when Neil deGrasse Tyson talks about this devastating detail of Mars, he is not trying crushing dreams. He is trying to anchor our thinking about the future in scientific realism, which is the only solid foundation on which to build genuine long-term plans. Because dreams not informed by physical reality are not visions. They are fantasies. And fantasies may be beautiful and inspiring, but they do not lead to practical results, only costly disappointments. And what we need now, more than Martian fantasies, is realistic long-term strategy for sustainable human presence in space that recognizes the real physical barriers we face, that invests in fundamental technologies needed before we try permanent colonization, that establishes infrastructure gradually starting with more accessible places before jumping to more challenging ones. And that always keeps Earth as an absolute priority, because even in the most optimistic scenario of space expansion, the vast majority of humanity will live on Earth for centuries. So ensuring that Earth remains habitable and prosperous is infinitely more important than establishing precarious outposts on other worlds. And perhaps this is the final synthesis of what we have learned. We have given about Mars and its devastating detail that the absence of a Martian magnetic field is not just an engineering challenge to be overcome. It is a teacher on the fundamentals of planetary habitability, a reminder that we are products of very specific conditions, an invitation to rethink our assumptions about space colonization, and a catalyst to more deeply appreciate the extraordinary blue planet we call home, because Mars, in its current reality, is not the romantic frontier that science fiction has painted it is a dead world, a planetary cemetery, a monument to the geophysical processes that determine whether a rocky planet may or may not sustain atmosphere and life on its surface. And there is a terrible beauty in that, a cosmic story told in desert landscapes and lethal radiation levels, a narrative of planetary loss, unfolding over billions of years. And by studying Mars, we are not just preparing to eventually visit it, we are learning to read the biography of worlds, to understand the delicate factors that separate oases from cosmic deserts, to appreciate how improbable and precious our own existence is on this particular planet, orbiting this particular star at this particular time in the universe. And that appreciation does not. It is pessimism, it is realism infused with wonder. And if there is real hope for humanity beyond Earth, it will come not from ignoring these hard lessons, but from integrating them deeply into our planning. To recognize that conquering the cosmos, if that is the right verb, will be the work of centuries or millennia, not decades, and that every step of that journey needs to be grounded in real science, in real physical laws, in real biological challenges, not in cultural narratives inherited from an era where we didn't know any better. So when we look at that red dot on the night sky, for Mars shining softly among the stars, now we see more than a colonization destination. We see a complex world with tragic history, with profound lessons to teach with, desolate beauty to offer, but with challenges perhaps insurmountable. At least in our generation, we see a cosmic teacher showing us through his own planetary death how special are the conditions that allowed life here on Earth. And perhaps this is the greatest contribution that Mars can make to humanity, not as our new home, but as our constant reminder to take better care of the home we already have. Because in the end, ultimately, the lesson of Mars' lost magnetic field is simple but profound. Some planetary gifts once lost may never be recovered. So while we have them here on this extraordinary Earth, we should treat them not as guaranteed unlimited resources, but as what really are rare and precious gifts of cosmic chance that made all we are possible, and that is something worth remembering every time we dream of other worlds.